Hi, this is Math 1650, and this video is going to be over our first chapter, sampling, and we'll go through section 1.1. With this chapter, there's going to be a lot of definitions that involve mathematics. We'll get more into math as we go through the chapters, but we do start out with just a lot more of a overview of why we're doing this math and what definitions are involved. All right, so let's get into this. First, we're going to look at context of data. And a lot of times you look in an algebra class or even a calculus class sometimes the context isn't always given in every problem. It's more about learning the procedures than why you're doing it. In statistics, context means a lot, because you're not just learning the procedures to how to do the statistics, you're learning how to analyze your statistics, especially in this class. Well, we're going to concentrate more on analyzing the data. So let's say we have two data sets, and we don't have all the values here, but just starting out, 112, 102, 110 for your X data set, and 114, 99, and 114 for your Y data set, and then so on. There's other numbers there. What do these data sets represent? Also causes us to want to ask important questions. So for instance, suppose these are husband and wife's IQ scores. That we may want to know, is there a relationship or correlation between the data values? Do women and men get together based on similar IQs, or is it kind of no correlation there, and that's not one of the factors that causes two people to get together? Suppose we have weights before and after some type of weight loss program. We may ask, is the weight loss program effective? And suppose that the weights are randomly selected New York residents and randomly selected California residents. We may ask, does one state have a higher average weight? Maybe one of the states introduced some kind of diet plan or something that became big, and we wanted to see if it actually had an effect on weights in that state. I don't know. There's more analysis that will go into. These aren't just the only questions we would ask, but it's a start of looking at context behind values. We also want to look at sources of data. So, for instance, we'll look at the consumer union. It's more of a unbiased source. That reports information. Whereas a clinical trial sponsored by a drug company is more suspicious. The drug company is invested in the research and probably has goals to have particular outcomes. So that's why a lot of companies will send clinical trials more towards third parties, research groups, or even colleges to actually conduct that analysis. Another very important concept is significance, and we're going to see two different types of significance. First type is statistical significance. This is where our math tells us whether we have something significant or not. And what we base it on is chance, whether results are not likely to occur by chance. If something's not likely to occur by chance and yet it's occurring, then it's statistically significant. If an event is unlikely to occur by chance and it does occur, then it's statistically significant, especially if you can repeat the study and get it to occur more than one time. So if we look at flipping a coin 100 times, if you get 52 heads out of 100, that's expected. All right, the actual expectation here would be about 50 out of 100. Sorry. I go back to screen sharing. Right, so if we're expecting 50 out of 100, 52 is not far off. It's caused because of just sample fluctuations. You're not going to actually get 50 out of 100 every time. But it's not unlikely. 97 out of 100 tosses, though, is very unlikely. And you don't expect to get that. That would mean that you would have to get a streak of a lot of heads in a row, and it's just not likely. And so if it does happen and you get 97 out of 100 tosses, then it's statistically significant. So the 97 heads out of 100 is statistically significant. When it happens. Because it's not likely to occur. Practical significance deals with whether or not there's actual practical purpose, right? And so practical significance thus, does the event have any purpose? Or is it worth the effort? There may not be any purpose in getting 97 heads out of 100 that would be practical unless you're working for a casino, maybe. But in many other research, sometimes getting something statistically significant is the goal or the most interesting thing about the research. Right, so let's say we have 40 subjects 1 year. And after 1 year on the Atkins weight loss program, these 40 subjects had an average weight loss of 2.1 pounds. Is this practical? And why? Okay. No, this is not practical because it's not enough weight loss in a year to be worth doing the program. Somebody could have 2.1 pounds fluctuate easily within a couple of days or a week. To have that as the average, you're pretty much saying you didn't really lose anything, even if it comes out that it's statistically significant. All right. So now we're going to look at some types of samples that can be considered bad samples or bad sampling methods, and what can happen with these samples. The first one is a voluntary response or self-selected sample. Here the participants choose to participate. And sometimes this is the only way, or you can't get around it. You can try doing sampling and other methods, but it still involves the participant sometimes stating whatever opinion they have or survey they need to fill out or something like that. But it can cause issues, and one of the main issues it can cause is this may lead to a sample that is not representative of the population. People with strong opinions are more likely to participate. You know, the surveys that you get for maybe a restaurant or a grocery store, you know, if you don't have any extreme experience, you may not fill that survey out. But if you do, then it's likely you'll fill it out. And a lot of times it's negative extreme. The next one is small samples. Small samples have a greater chance of random error. These values then might not target the population values. think about flipping a coin. We know the coin has a 50% chance of being heads. You flip it once, it's either going to be 100% chance that you got heads in that first flip, or 0% chance you got heads in that first flip. It's never going to be 50. You flip it twice, there's a chance it could be 50. You get one heads, one tails. There's also a chance it could be still 100 heads, two heads at the same time, or one right after the other, or it could be two tails that you got. So, either one of those is all likely possible. But the more you flip it, the more it's going to narrow down the likely outcomes that are possible, and those are going to be closer and closer to your actual value. All right, so one good thing about this is, if you're doing small sample sizes to begin a study, that doesn't mean you can't keep repeating the study, increasing that sample size. But small samples are always the best. But we do have ways in statistics to help decide what sample size you actually need. Now, some other things: exaggerated graphs. Right, these are graphs that misrepresent the data. And make changes appear dramatic. Or insignificant. One of the common things is if you have, let's say, a bar graph, and on this graph, let's say you have two bars. Let's say this is a true value, and so one bar may be higher than the other, but it's not a drastic difference. Right? But if you change the scale, maybe that doesn't start at 0, maybe that starts at 90 to 100. So you have the bar that's still at 100, but this one, you say that's 95, all of a sudden it looks half the size, even though it's really just 5 units lower. The next one is very similar, but with more pictures. Sizes of images may not be proportionate to data changes or data differences, misrepresenting the data. Common one here is you have a dollar bill and it represents a certain value, let's say $1,000, and they want to show it doubles, but they double it in both directions. But now it actually looks like it quadrupled instead of doubling it in one direction. So the correct way of doing this would be maybe just to go vertical. Doubling it gives you a second dollar bill above it instead of also one to the side. And so this happens in areas a lot of times when they're trying to show maybe a length has doubled, but they're doubling the area. So picture graphs and sometimes misrepresent data, and sometimes it's just an accident. Somebody thinks they're being creative and they're not seeing that they're causing an issue. Um, some other things, some stuff with surveys, loaded question. Purpose is to influence the respondent's answer, leading to a bias result. That means on a survey they ask a question in such a way where you're not going to want to answer it the way they don't want you to answer it, because it sounds bad, even though maybe that is the truth of the answer you actually will want to choose. Order of questions can be an issue. The sequence of questions can lead to bias and influence later answers. This also goes with order of answers. If they have the answers in all different orders, then it's more randomized. But if they have certain answers at the top, certain answers for C, certain answers below, people may get into just doing patterns or whatnot. Another big thing that can happen, especially what goes back to the voluntary response one, is refusals. Having missing data can cause the sample to be non-representative. Having missing data can lead to samples that are not representative of the population. This isn't something a researcher may not be able to avoid. Sometimes it just happens. People drop out of studies. People can pass away. People can just choose not to continue. And so sometimes that data has to be is missing, and the researcher has to make a decision on how to handle that. Then there's also interpreting causations that can lead to a problem. Correlation does not mean causation. It also doesn't mean that it's not a causation. Okay, there's actually three possibilities. There could be a cause. One variable could cause another one to behave a certain way. There could be a coincidence where multiple studies help eliminate this issue. It's coincidence, it's not going to keep happening. And then there could be an underlying factor. And so between the cause and the underlying factor, that takes some critical thinking, some studying, some research, not necessarily statistical research, but research about the two things and whether there could be something that is an underlying factor. For instance, if gas prices and diesel prices go up, one is not causing the other one to go up. They both have an underlying factor of oil prices going up. Then we have self-interest studies. This is studies conducted by an organization that has a vested interest and can lead to bias or manipulation. of the data in the interest of the goals. A couple more precise numbers. This is something like saying, there are 400 million, 450 million, 500,002 houses. We don't know the exact number in the United States. What happens is it gives a false sense of accuracy, where rounding or estimating is more appropriate. Because the value may not be as certain. Even if we've done studies and we get a certain average, that average still has a margin of error there. Right. Partial picture can give a skewed view of the issue or the situation. Believes out important information. I always use an example in my class that last semester I didn't fail anybody in statistics. But what if I'm leaving out the information that I didn't teach statistics? It changes the picture if you have more information sometimes. And the question is, sometimes maybe we don't have the information because we just can't obtain it right now. So, in a study, what you do is you have to note that, so it's aware that people are still thinking about it, and the research is still thinking about it. And then probably the worst thing, deliberate distortion, misrepresenting data in some unethical way. And done deliberately. This can lead to bad and harmful decisions. Right. The last thing we'll get into, or the last one on here, of these bad samples or things that can cause issues. We're also going to go into how do we do this correctly so it's not an issue. And that is percentages. Percentages can be misleading and not understood when they're not based on correct methods. So can be misleading and not understood, especially when based on inappropriate sample size. All in all, we just have to watch out that percentages are not of how we handle percentages, basically. So we have a formula for finding percentages for a survey where you have X amount of people who state a certain idea or opinion or whatever out of a sample size. N is your sample size. X is the people stating whatever X is, X opinion or X value. And then P of X is that probability or that percentage or proportion for that matter. So it doesn't have to be probability, but you can think of it as a probability, but you can also think of it as a proportion. So let's say we did a survey where 52% of 1,038 surveyed adults said that secondhand smoke is very harmful. What is the actual number of adults who said that secondhand smoke is very harmful? So we have the percentage, we have the sample size, we need to find what X is. So sample size is 1,038. Percentage, we have to write the percentage as decimal here. Percentage is 0.52. We get 539.76. Since we're dealing with people, we're going to round up to 540. Now this is different than if we were to say 52 people said that secondhand smoke is not at all harmful. This would be, well, X is 52, N is 1,038, so our percentage or proportion is 52 over 1,038. You get 0.05 or 5%. Okay. Remember, to get a decimal into a percentage, you multiply by 100 or move the decimal 2 spots. If you want to get a percentage into a decimal, divide it by 100 and move the decimal 2 spots. Remember, for proportions and probabilities, we're looking at the percentages are a decimal under 1. Now, let's look at the context of both of these. First one was 52% said that secondhand smoke is very harmful. So 540 people or 52% of the surveyed people said that secondhand smoke is harmful. In the next one, 52 people or 5% said that secondhand smoke is not at all harmful. Underline not harmful. Okay, so two different contexts here as well, besides the two different ways of doing two different ideas of how you look at a percentage. So you gotta always go back and look at the problem and see what you're actually answering here, and not just do the math. Alright, in the next section, we'll do it, it'll be on another video, but we'll go into 1.2 and we'll look at types of data. I'll see you then. Bye.